All right, so let's go ahead and look at some of the information necessary to work on the module folder 5C pre-lab for beta decay. This is another one that is technically a emulated simulation. It's from a different file format, which is not well supported anymore, but they're able to allow us to still work with these. Okay, so link to the simulation, and then basically we're going to look at the stuff around it and play with the settings as each question describes. So there's not really a base set of instructions. Okay, so it asks what happens when hydrogen 3 turns into helium 3. So if we check the simulation, hydrogen 3 is here, helium 3 is there. It might be easier if you can zoom in or maybe take a screenshot and zoom in on that, but I think we can just barely tell. Hydrogen 3, it has the hydrogen here and 3 label in the front. Well, 3 means that there's 3 total nucleons, 3 particles inside the nucleus. Hydrogen is the first element on the periodic table, so it has an atomic number of 1, which means it has 1 proton. If we look at the key, red, proton, gray, neutron. So there's 1 proton and 2 neutrons. Okay. Now through this process, this beta decay, because that's what it's called for the lab, we turn from hydrogen 3 to helium 3. We're not technically gaining or losing any overall particles from the major pieces. What we're going to see from this, from our major nucleons, basically is that one of them transitions into the other one. So either a proton switches into a neutron or a neutron switches into a proton, depending on what type of beta decay there is. So notice that at the beginning we had 2 grays and 1 red, and now we have 2 reds and 1 gray. It looks like we gained a proton. So let's read the choices and see what that seems to tell us. Well, it doesn't lose a proton, right? It almost seems like it gained one. There's nothing about electrons in any of this. I mean, there's a little blue dot, but notice there's no blue dots in this part. So be careful with these 2 choices. The neutron transitions into a proton. That's the one we want because the proton seems to, the number has seemed to increase, and the neutron number seemed to decrease. Okay, then the name of this, be careful because it's asking for the specific name. And so beta decay is actually a category of types of reactions. This is beta minus decay or beta negative decay. Different names for the same thing. Okay, so we want to use a bunch of these. We have a bucket of atoms. So we're going to do a whole bunch of hydrogen 3s, watch them decay, and then see if we can answer some information. So how many do you expect to have decayed after the first half-life passes? Well, by definition, half-life is the statistical average amount of time that it should take for about half of this stuff to break down. Now, technically, I can't get to 100. It caps at 99. So if you do the math, you'll see it's not perfect. But I'm going to go with half-life, and I expect it to be roughly 50-50. It's a random process and a statistical average when we're dealing with that half-life number. So usually it's not going to be perfect, and we actually can't take half of 99 again because rounding error. So this is still reasonably close. If we look at our choices, those are thankfully far enough apart that it shouldn't be an issue. Around half have decayed, right? So the ones that have decayed, they went from the purple hydrogen to that pinkish helium. Okay, so then the next question, how many do you expect to have not decayed when 25 years have passed? So let's let it keep running. We'll get to 25 years, which is roughly the middle here, and then let's talk about why that's potentially important and what it looks like. So coming up on 20 here, we get to 25. I'll see if I can pause. There. Okay, so what's important there, and I may have slightly overshot, so maybe it's a little bit back here. The half-life is something like 12 or 12 and a half based off of what this picture shows. Something you can look up if you want to know the exact number. But if we double that, then we should get to about 25. So where you have to be careful with the half-life is that a half-life, again, is the statistical average that it takes for about half of material to decay into something else. But if another half-life passes, it doesn't mean that the other half of the material has decayed and is gone. It means half of what was remaining after the first half-life. And that's where this gets tricky, is it's half and then half again and then half of that and then half of that and so on. So it becomes an exponential process. Something that you see an example sometimes in a pre-calculus class when you're learning about special functions. But for us, we started with 100 hydrogens approximately. Then after one half-life here, we expected to have 50 left and 50 that had decayed. Then in the next half-life, the 50 greens we would have had left, we expect about half of those to decay. So 25 hydrogens roughly should be left, and 75 should have turned into something else. So let's read the question one more time to make sure we answer carefully. The ones that have not decayed. So how many are still hydrogens? Well, this is 21. Again, it's not perfect. It's a random process. And that's going to be our closest choice. All right, so unfortunately, unless my eyes just can't tell, between carbon and nitrogen with these bundles, I can't see which particle is specifically different. Unless it's like behind the 14 or something. Like I don't know. I can't tell specifically which one of these is different. But if you were to draw them out or check a periodic table and check the number of protons, I will tell you just as a hint, and because of how the assignment is set up, it's exactly the same kind of decay, right? So we can't see it as clearly in the picture, but it's the same thing happening with these two as what happened between hydrogen-3 and helium-3. So from that, we say that a neutron transitions to a proton. Again, look up the atomic numbers. You can see that it looks like we would have gained a proton, and that's the only answer choice that reflects that. We named this earlier, so same thing as it was on question 2. Because of the ambiguity in the picture, almost free questions here if you just remember what was going on for the first 2. Okay, so now we're going to switch elements. And we want to watch the first half-life. Okay, so remember from before when we switched, or rather when we started the first half-life, about half of the material broke down. We expect this to be somewhere around 50-50. The difference now is that a half-life is something like 6,000 years. It's different for different elements. Thankfully, we don't have to wait 6,000 years for this to finish, because it's obviously sped up by quite a bit. If we look, 4752 is reasonably close to 50-50, so it doesn't really matter in this case what we're looking for. First half-life should always make about half the stuff go away. And half the stuff is left. So that's what we answered this time. Okay, now the next question is asking about what happens after 18,000 years. So 18,000 years, if one half-life is about 6,000 years, then 2 half-lives would be about 12,000, and 3 half-lives would be about 18,000. So essentially, we want to watch this until it finishes to more or less the end of the graph. It's hard to tell exactly where 18,000 would be, maybe somewhere like here, and we want to see what's left. So we've already passed for sure where the second half-life would be here, and so notice we've got similar numbers to what we had before. We expect to have roughly 25 of the original and about 75 of the new thing, but we're going to keep going. And so out of those roughly 25 that were left, we expect about half of those to decay. Well, random process. Notice that nothing dropped for a while. And my best guess, this is somewhere around where 18,000 years would be. So let's read the question one more time. How many have decayed for 18,000 years? So that's the new stuff, right? That's the orange slice, big sector of the circle. That says 83. In theory, technically the exact number should be something like 87.5, but this is 83. It's reasonably close. None of the other answer choices are even near this number. So there we go. Be careful with this though. If you don't read carefully, the ones that have not decayed, there's roughly 12 of those left. So always reread the question before you pick your answer. Okay, so we have a custom element where we can dial in whatever we want the half-life to be, right? So I'm gonna add a bunch of elements. Let's read the question and see what we're gonna do with these last 2. I want 100 atoms to turn into 25 atoms after 30 years. Okay, so let's reason through the steps here because that's kind of a lot going on. 100 atoms are going to turn into 25 atoms. So remember that in one half-life, we're going to go from 100 atoms to 50 atoms, right? 50 will decay, they'll turn into something new, they'll be gone. They'll be what are called daughter particles. And then a decent chance that those decay and turn into something else later. But that's a different assignment. Then the next half-life means that of the 50 that were left after the first half-life finished, half of those are going to decay. So 50 gets cut in half again by the second half-life, and there should be about 25 left. So estimating through those numbers, we expect roughly 2 half-lives to have passed. Okay, well, if we want 2 half-lives to pass in a total of 30 years, then 30 divided by 2 sounds like 15. So let's see, maybe about here. Let's see if that works. All right, so for the first half-life, again, we expect to get to roughly 50-50 on this part. And I'll pause it somewhere close, and we'll check to see if it even kind of worked. Unless it drops a bunch, it's not looking... I mean, actually, we got the opposite numbers earlier. Like I said, random process. So we have a little bit more left that have not decayed than what we would usually expect, but it's still in range, right? So now, of those 54 that are still the original custom element, which, you know, looks suspiciously like the same exact picture carbon and nitrogen had, but I guess we're not going to talk about that. Half of those 54 should decay. We expect this to come down to be, you know, around 27 from this number, but on normal average about 25 by the time it gets to that particular line. So let's see if it actually works this time. We can see them decaying, shooting out pieces. We're getting, you know, most of the way through that second half-life. It's actually not looking too bad. Kind of missed clicking on it. It was close. We said something about 25, 75, you know, should have been what we saw. And it's possible I wasn't perfectly in the middle here. And, you know, it's random, right? For our revised guess, they said there'd be about 27 there. That seems to have worked. So I think we can confirm from one sample. And if you're not confident, you can always just try it again and see if it works better the next time. Okay, then one more. Set the half-life to the custom element to 2 years. So that's really hard to tell. Maybe, yeah, let's use that as a trick. Like right when the time unit disappears, right there. So that's roughly one half-life. Maybe there. I don't know, it might be slightly past. So again, about half the stuff is decayed. We want to go to 10 years. So by 10 years, several half-lives would have passed. So let's think about it. You know, I have no idea what I actually drugged this to. It doesn't give us more information, but let's say that this is about 2 years. So another 2 years would be another half-life. Another 2 years would be another half-life. Another 2 and another 2 would be another half-life and another half-life. Well, that's a total of 5 half-lives by the time we get to 10 years. Okay, so 5 half-lives would mean that it cut in half, then that cut in half, then that cut in half, that cut in half, and finally that cut in half. There would be very, very, very little left. If we estimate, say we started with 100, then we'd get to 50, 25, like 12 and a half, 6. Like you can see where it can get real small. So if we look, let's read the question. How many have decayed? Okay, so those are the black ones that turned into something else. We've got 93. 93, yeah, it's close. All right, that wasn't too bad. But basically, you think about how this one's set up, you probably think it should be the biggest number anyway, and none of these are even close. There's a chance between, you know, random samples and exactly where this gets placed and when you click pause, there's a chance that they're all gone by the time you get to 10, right? So if we look, it's random how long it takes. There is a period of time where there's just no more left. All right, well, that should be it.